This lesson is for section 6.12 in our textbook. We're going to be talking about inverse functions today. We're going to begin by graphing a few functions, and then we're going to actually determine if a function is an inverse of another function, and then find the inverse of a function. So those are our main objectives for today. So I want to start out first by having you guys sketch this log here. So you guys can pause the video here and try to fill out this completely on your own, just to get good practice with this, because of course you are supposed to be able to graph log equations now. So please pause and try question 1, as well as question 2 here, which says on the same graph you're going to graph this exponential function here as well. Okay, so please go ahead and pause the video and fill out this information. Alright, hopefully your graph looks just like mine. In blue here I graphed the log function, and in red is the exponential function. So the reason why we're starting off with this review, because this is something that you've already done, you've already seen how to graph log functions and exponential functions, but we're studying the topic of inverses today. And I know I've said it before in class, but the inverse of a log is an exponential function, and the inverse of an exponential function is a log function. So what we're seeing here is graphically what it means to be an inverse function. Now if I take a look at some of these coordinates here, like for example this x-intercept 1, 0, on our exponential function that coordinate becomes 0, 1, and it's now the y-intercept. If we look at another point on this graph, let's say this coordinate 2, 1, that coordinate is 1, 2 on our exponential function. So here, where it asks how are the two graphs related, similar, and different, we've got lots of things we could say here, but one thing that mainly stands out, even if you just look at the tables, our coordinates switch. Okay, our coordinates end up switching, and that's very interesting. I think the fact that the y-intercept switches as well. You can think of it as a switch. It's not really going to stay the y-intercept, right? The y-intercept becomes the x-intercept on the other graph, and we see the domain and range is different when we look at one graph to the next, and the asymptotes also kind of switch, but they're all very related too in the same way. So if you want, in your own words, go ahead and explain here how these graphs are similar and different to one another. Alright, we're going to continue with this graphical approach to understanding what an inverse function is. Now, not every function has an inverse, so a function has to be one-to-one in order for it to have an inverse. Okay, so let's explain what it means to be one-to-one. Now, earlier in the year we talked about what a function was. Remember, this is where every x has exactly one y output. That was the whole birthday idea. Each person can have one birthday. Even though two people can share the same birthday, one person cannot have more than one birthday. So this is how you're seeing a few different x's sharing the same y, but each x has exactly one y. Now, a one-to-one function is still a function. So here we can see it's still a function. For every x there's exactly one y, but it's more than just a function, because it also has that every y has exactly one x. We could go backwards here and say, oh, okay, -2 here only maps to 7, 5 to 2, and 8 to -1. So a one-to-one function means that for every x there's only one y, and for every y there's only one x. Alright, so the easiest way to tell if a function is one-to-one is actually to look at the graph of the function and see if it passes something called the horizontal line test. So I know that we've talked about the vertical line test before, and that was just to test whether or not a function is a function. The horizontal line test, though, tests whether or not it's a one-to-one function, so it's the same idea. If I were to draw a horizontal line through that blue function here, I see that it only intersects exactly one spot, so it passes the horizontal line test. So that means that the blue line here is a one-to-one function. So I've got our function, I'm going to call that f of x, and I've got another function here graphed, g of x. Now these are inverses of one another. So if you take a look at the coordinate 0, 3 here, that coordinate becomes 3, 0 on the graph of its inverse. Now you're also seeing this other dashed line here. This is the line y equals x. Okay, so this is the line y equals x. Now when you graph a function and its inverse, it's reflected over the line y equals x. So every coordinate here becomes reflected, like this is sort of like a mirror, okay, and you're seeing a mirror reflection between f of x and g of x about the line y equals x. So if we look at another picture here, in blue here, let's look at the function f of x. So f of x here passes the horizontal line test again, because everywhere I draw a horizontal line, it only intersects that graph one time. Now we see the graph of its inverse. Let's call that g of x here. There's our inverse, drawn in red, and it looks exactly like the same graph here, just reflected over the line y equals x. So these are inverses of one another. So we have a function as well as an inverse function, because this is a one-to-one graph. Now, the next picture here, it is still reflected over the line y equals x, right? We're seeing a picture of this blue function here, and then this red graph, it's not actually a function, it's a relation, okay? It does not pass the vertical line test, which means that this is not a function. Now, even though the graph of this picture here does have an inverse, because you can reflect it over the line y equals x, it doesn't become an inverse function, because our original picture here, let me erase this, our original blue graph does not pass the horizontal line test. So our function here, f of x, let's call this f of x here, this is not one-to-one. Okay, because that means, basically, remember we talked about one-to-one means that for every x there's only one y, and for every y there's only one x, but here you can see the same exact y value, right? This line y equals 5 here intersects the graph twice where there's two different x values. So f of x is not one-to-one, which means that the graph here, g of x, is not a function. Is not a function, not is a not function. So is not a function. Function. Okay? So g of x is a relation here. So that's just a general idea for what a function is and what an inverse function is. Alright, now keeping with this whole graphing idea here, we're going to graph a function as well as its inverse. So here I have a function. Now I'm using function notation. Instead of using y equals 3x, I'm using f of x equals 3x. So I've already filled out the table of f of x. We're going to do this one in blue. And then I'll graph the inverse function here. We don't even need to know what the function's inverse is, because we talked already about how the coordinates x, y become yx on the graph of your inverse. Now, I am using a new notation, though, that we haven't seen before. So we use this little notation here. It's kind of like your exponent here is -1, but this is out loud read as f inverse x. So f inverse x. Okay? That's our new notation. So in order to get those coordinates, all I have to actually do here is just flip them. So I have -6, -2, -3, -1, 0, 0, 3, 1, and 6, 2. Now if I graph this first portion here, actually I want you guys to go ahead and pause the video and go ahead and graph that real quick. I'm going to do the same. Okay, so here you go. Hopefully you did pause and try the problem on your own, but here I've got the two graphs. So you can clearly see that both of these are functions, right? They both pass our vertical line test, and they are also reflected over the line y equals x. So here if I draw on that line y equals x here, you see that these are mirror reflections of one another about the line y equals x. So this is how you would graph a function and its inverse. You simply switch your coordinates. Pretty simple, right? Now in the next question, I'm going to start off by just reviewing here how to graph this square root of x, and then I'll let you finish off the problem. Now when you graph the square root of x, remember you can't use your standard table of -2 to 2, because if I try to plug in -2 here, I end up with a non-real answer. So I'm not going to use those values here. Now taking the square root of 0, that's pretty easy to do. I get 0, and taking the square root of 1, I still get 1. So those are all very easy points for me to graph. I don't want to pick 2 though, because taking the square root of 2, that's not such an easy value for me to graph. So it's not very exact. I don't want to use that one. So in this case, it's actually probably more helpful to pick out your y values, just like we did with the log function, so that you can find nice values for x. So I would pick a y value of 2. Well, how do you get an output of 2? What do you have to take the square root of in order to get 2? Well, that number would be 4. So you're just picking perfect squares here. So obviously the next coordinate would be 9, 3, you know, and then 16, 4. So again, it might be helpful to take your y values first. Now for your table here, I'll let you guys finish graphing your inverse function as well. So please make sure you pause, check with the key, and try that one on your own. Okay, now in the next portion of our lesson, we're going to switch gears a little bit. So far we've been looking at inverse functions from a graphical approach. Now we're going to take a look at it from an algebraic approach. So here I've got the definition of an inverse function. So it says that two functions, f and g, are inverses of one another if and only if f of g of x is equal to x and g of f of x is equal to x. So what this is saying is that we're taking the composition of f and g and testing to see whether or not that is equal to x. Then if we take the composition of g of f of x, we want to see if that is equal to x as well. So this is composition of functions. Now we did this, I think in first semester, I forget which chapter, but this is just the composition of two functions. So we'll review this notation here, but basically whenever it asks you to determine if you have an inverse of a function, you want to test this statement here. You have to test both cases though, okay? So this is this might be asked, you know, prove that the following are inverses of one another, or determine. It could be either way. But basically you want to test, is f of g of x equal to x, and is g of f of x equal to x. So those are the two cases that you need to show. So let's start with showing f of g of x. So I'm going to use the notation f of g of x. So remember, that means that you're taking the function f and you're inputting g of x into that. So f of 2x plus 8. So we know from before that all this means is you're inputting this in for the x here. So this is going to turn into 1/2 times 2x plus 8 minus 4. If I multiply this out and simplify here, I have x plus 4 minus 4, which is indeed x. So that means f of g of x is equal to x. So I'm just bringing this side down here. Now I need to also test, is g of f of x equal to x? So in this case, I have g of f of x is 1/2 x minus 4. So I'm inputting this into g. So I have 2 times 1/2 x minus 4 plus 8. Okay, so I'm just inputting it right back into here. If I simplify here, I have x minus 8, right, distribute, plus 8, which is equal to x. Therefore, g of f of x is also equal to x. Oops, not equals, equals. So I'm just bringing down that left-hand side here. So because both of them are true, f of g of x is equal to x and g of f of x is equal to x, these are inverses of one another. So yes, they are inverses. Okay? Alright, so I'm going to erase real quick and then we'll try problem B. Alright, now in problem B here, we want to see if f of g of x is equal to x and g of f of x is equal to x. So again, if you want to try this one on your own, pause the video and check, you're more than welcome to, because I think it's important that you understand the notation here. But I'm just going to solve through this whole problem with you guys. Alright, so we start with f of, we're inputting x over 3 plus 1, right? This is our g of x here. That's going to be substituted in here. So now I have 3 times x over 3 plus 1 minus 1. If I test here, I end up with x plus 3 minus 1, which ends up giving me x plus 2. So in this case, f of g of x does not equal x, okay? Which means that these are not inverses of one another. So I don't even have to test the next one because I've already seen that the first one here doesn't hold up. So these are definitely not inverses of one another. Okay, the last portion of this lesson is to find the inverse of a function algebraically. So instead of giving you a graph and asking you to graph the inverse, now we're going to give you a function here and ask you to algebraically find the inverse of that said function. So this isn't too bad. It's actually pretty easy to do as long as you follow these 4 steps here. The first step is to use x and y notation instead of function notation. So I'm actually going to go back here, and instead of writing f of x, I'm going to write that as y equals 2x plus 7. Because remember, f of x is equal to y. So I changed it from function notation to just, x and y notation. Now the second step is probably the most crucial here. You have to make sure that you exchange now your x and your y. So I just write that as x equals 2y plus 7. So again, I'm just exchanging where I put the x and where I put the y. Now, here's where the algebra comes in. Now you're going to actually solve for y. So here was step 1, here was step 2. Step 3, go back and try to solve for y. Isolate the y. So I would subtract 7. So I have x minus 7 equals 2y. And then I would divide the 2. So that I end up with y equals x minus 7 over 2. And I'm just going to write that y out in front. Okay, so I have y equals x minus 7 over 2. So that's step 3. Now, step 4, you're going to replace it now with inverse notation again. So you're going to go back and instead of writing a y here, you'll write that as f inverse x. So f inverse x equals x minus 7 over 2. So this is the inverse function of 2x plus 7. X minus 7 over 2 is the inverse function of 2x plus 7. Let's try number 3 and 4. I'm going to let you guys go back and try number 2 after we do 3 and 4 together. So in number 3, the first step, of course, here is to use x and y notation. So I changed this to y equals 5 to the x. And now I'm going to switch the order. So that was step 1. Step 2 is switch the x and the y. So we have x equals 5 to the y. Now step 3 is to solve for y. Now this is this is an exponential function and we're stuck, right? If we want to solve here, we have to actually switch forms and make this into a log. So I have log base 5 of x, the argument, equals y. See how y is now solved for? So I just did step 3 all in one step by just switching forms to a log, which is why you're also seeing that the inverse of an exponential is simply a log. Okay? So it all kind of ties in together. Now I want to replace in step 4 that y here with f inverse of x. So I have f inverse of x equals log base 5 of x. So this is the inverse function here. This log is the inverse of 5 to the x. Now in number 4, don't think of this as being any more difficult than the problems that we just worked on. It's starting off by giving you the inverse, and it's asking you to find basically f of x. So we're trying to find f of x if we are given f inverse x. This doesn't change how we do this problem. We would still follow step 1 here, where we're going to use x and y notation. So we have y equals 6 plus log base 3 of x. Now I'm going to switch so that's step 1. I'm going to switch now and exchange the x and the y. So I have x equals 6 plus log base 3 of y. Okay, and now I want to solve for the y. So I want to isolate this y. The first thing I need to do is make sure I move everything else away from the y. So I'm going to get rid of that 6. So I have x minus 6 equals log base 3 of y. So I'm stuck right now in this log. We know we need to switch forms. So I now have 3, that's my base, to this exponent here. 3 to the x minus 6 is equal to my argument y. So I just solve for y here by switching forms. So not too bad. And again, you're seeing that now the exponential here is the inverse of this original log function. So the last thing to do is to replace this with f of x notation. Now because we've already seen what the inverse is, we want to find what the original was. I'm going to use f of x here. So I have f of x is equal to 3 to the x minus 6. And that is the original function if this is its inverse. Alright, that's the end of the lesson. Please go back and try number 2 on your own. This one's a little bit easier, I think, to do than the other ones. That's why I picked those ones to do with you. So please go back and practice that one and check with the key. Nice job. I will see you tomorrow.